Good evening, all. Uh, Welcome to the live interaction session for week 7 of our course, Computational Fluid Dynamics by Professor Srinivas Jayanti, Department of Chemical Engineering, IIT Madras. I am TA Manjunathan, Research Scholar in the Department of Applied Mechanics and Biomedical Engineering, IIT Madras. So, in week 7, uh, we have mostly in last weeks we have discussed on the basic concepts of CFD. There were errors existing in it, the types of errors which can occur, and what are the criteria for stability, consistency, convergence, and all those things. From in week 7, we are discussing about solving the Navier-Stokes equation, particularly in the viewpoint of compressible flows. What are the special schemes that are available there, uh, which may be less discussed but having significant role for solving compressible flows. Such schemes like McCormack scheme, beam warming methods, all such methods and its intricacies have been discussed in this week's 7 lectures. Hope everyone has gone through the video lectures. So let's move on to our uh, questions. So I will present the questions and read it out for you. Take some time to think and try to answer the question, and you can inbox your answers. So question number 1: explicit schemes are generally which of the following? Option A: more computationally expensive than implicit schemes. Option B: less stable than implicit scheme for solving stiff differential equations. Option C: always unconditionally stable. Option D: not suitable for solving system of equations. So the question is on difference between implicit and explicit schemes. So the uh, question is asking for the general expression for explicit scheme. So explicit schemes are generally which of the following? Option A: computationally expensive than implicit schemes. Option B: less stable than implicit schemes for solving stiff differential equations. Option C: always unconditionally stable. Option D: not suitable for solving system of equations. You can try to answer the question. Our answer is uh, option B. That is less stable than that is explicit schemes are less stable than implicit schemes for solving stiff differential equations. So uh, generally, I think everybody know what is difference between explicit and implicit. So in explicit schemes, all the variables are explicitly uh, known, or maybe we will be taking all the variable values of variable will be taken from uh, a previous iteration. So all values will be taken, but in implicit schemes, uh, schemes will take a lot of values from the current iteration steps. So all plus current will be mostly in implicit schemes, or dominance will be for current values. So and what's this stiff differential equation? In stiff equations are kind of unstable system of equations, and which may be so stiff differential equation in this aspect are kind of a little unstable system of equations that may need uh, really smaller time steps for its convergence. So in that case, uh, explicit schemes will be become really unstable if we are using explicit schemes to solve this stiff differential system of differential equations. Whereas implicit schemes give an advantages in such conditions with smaller time steps. Implicit schemes can help to solve this stiff system of equations, stiff differential equations, uh, in a better way. Moving on to next question. In a finite difference scheme, a higher order approximation of the derivative often leads to which among the following? So the question is on in an FDM scheme, finite difference scheme, higher order approximation. What will be the effect of higher order approximation? Options are option A simpler and less computationally expensive scheme. Option B, increased stability of the scheme. Option C, a more accurate solution but potentially less stable scheme. Option D, no change in the convergence properties. So the question is on what will happen if we are taking an higher order approximation for uh, higher order approximation of a derivative is taken. Answer is option C. That is, uh, a more accurate solution, but potentially less stable scheme. So this is our answer, option C. Because when higher order approximation, that is, we are neglecting only higher order terms and keeping so for while approximating to certain terms, we know that our dou square 5 by dou square n can be written as some terms plus some higher order of terms. So when we are neglecting only these higher order terms, or we are taking some higher order approximation for our derivatives, the as we know, the truncation error will be less. That is, um, we are only what truncating or excluding uh, the higher order terms which are having very less value. It will be very small decimal values. So neglecting or truncating these effect will make the solution more accurate. But we can see that there will be, suppose we are taking 0, 1, 2, like up to second order we are taking here, then there will be three times only to address this particular second order derivative. Suppose we are even taking for third or fourth order terms, then there will be five times only to represent this derivative. That will make the scheme less stable. So that is what the complexity. While we going to higher order approximations, we will get a more accurate solution. But there are the direct implication of is that the schemes become less stable. Then we will have to add another methods to make the scheme stable. So that's one particular challenge we will face when we will have to go for higher order approximation. But when we are taking second order or first order, that is the trade. The stability is the trade that we are giving for accuracy. Moving on to next question. In this week's last week's lectures, have extensively discussed about McCormack scheme. The question is on McCormack schemes. The question is, the McCormack scheme is particularly useful for which type of equations? So the question is on the type of equations suited for McCormack scheme. Options are: option A, elliptic equation; option B, hyperbolic equation; option C, parabolic equation; option D, all of the above. So try to reflect whether there is a uh, choice of equations for using McCormack scheme, or it is just can be used on uh, any kind of equations. Try to answer the question. Our answer is option B, that is hyperbolic equation. So McCormack scheme is particularly useful for hyperbolic equations. That is a simple question. Moving on to next question. In the McCormack scheme, the predictor step uses a scheme that is inherently which of the following? Options are option A, stable but not dissipative. Option B, dissipative but not stable. Option C, both stable and dissipative. Option D, neither stable nor dissipative. So the question is on particularly on the predictor step of the McCormack scheme. So what does the predictor step provides to the equation? So as we know, this McCormack scheme has two steps. That is, first one is predictor step, and second is corrector step. So the question is on the predictor step of the McCormack scheme, and which of the following is the quality of the predictor step provides. Our option is option C, both stable and dissipative. By giving a predictor step, that we will try to make the uh, scheme more stable, also dissipative. And as we have already mentioned, this McCormack scheme is used for hyperbolic equations. Moving on to next question. This is on the second step, that is the character step of the McCormack scheme. The character step in the McCormack scheme aims to do which of the following? Options are option A, reduce the dissipation introduced in the predictor step. Option B, increases the dissipation for stability. Option C, improve solution accuracy. Option D, all of the above. So the question is on the second step, that is the character step in the McCormack scheme. And what is the idea behind the character step in McCormack scheme? Our answer is option B. That is, correct step increases the dissipation for stability. Moving on to next question. Next question is a major advantage of McCormack scheme compared to Lax-Winthrop scheme is. So the question is on comparison between McCormack and Lax-Winthrop scheme and the advantage of McCormack scheme over Lax-Winthrop scheme. Options are option A, it is unconditionally stable. That is, it does not need any conditions to become stable. Option B, it is less computationally expensive. Option C, it has higher formal accuracy. Option D, it is better suited for steady state problems. We have discussed Lax-Winthrop scheme in the previous weeks. So try to recollect and try to answer the question. What is the advantage of McCormack scheme over Lax-Winthrop scheme? Option B, that is, McCormack scheme is less computationally expensive. That is our answer. That is the main advantage of McCormack scheme over Lax-Winthrop scheme. So where Lax-Winthrop scheme was uh, discussed last time, the complexities there. So McCormack scheme is introduced to make it less computationally expensive, and the steps are split between to reduce the computational thing. We are giving a predictor and corrector steps. So that uh, prediction correction cycle will help to stabilize our solution. Moving on to next question. Next question is, a disadvantage of McCormack scheme is that it is, options are, can be overly dissipative for some problems. Option B, it is difficult to implement for some complex geometries. Option C, it requires excessive boundary condition treatment. Option D, all of the above. So, which of the following is a disadvantage of McCormack scheme? Question is really intuitive, and from the previous questions I have discussed today, it can be simply seen that the answer is option A. It can be overly dissipative for some problems. That in we have seen that in it has two steps, that is character and predictor, and both character and predictor steps sorry, both predictor and character steps in uh, includes dissipative property or introduces dissipative property. So this uh, inclusion of dissipative property by the predictor as well as the character steps makes the McCormack scheme overly dissipative for some problems. That's a disadvantage of this McCormack scheme. Moving to next question. Next question is on beam warming scheme. In what context might the beam warming scheme to be used within a multi-grid algorithm? Options are as a coarse grid solver, option B as a fine grid solver, option C for residual smoothing, option D not applicable in multi-grid methods. So the question is on the question is on beam warming scheme. So if we are using beam warming schemes in a multi-grid algorithm, then which grid should be solved by beam warming method? Option A coarse grid, option B fine grid, option C residual smoothing, option B not applicable in multi-grid. As we know, beam warming method is an ADI scheme, that is alternating direction implicit scheme, and this beam warming method is also used for hyperbolic equations. And in a multi-grid equation, it is mostly used as a coarse grid solver. Option A is our answer. So for a multi-grid solver, beam warming method will be used as a coarse grid solver. Moving on to next question. In the context of numerical stability, what does numerical dampening refers to? So the question is on, we have discussed what is numerical damping in previous sessions. So the question is on, uh, from the point of view of the numerical stability, what does numerical damping refers to? Options are: option A, reduction of high frequency errors that may not represent physical solution. Option B, amplification of low frequency errors that become dominant over time. Option C, introduction of artificial source time in the discretized equation. Option D, elimination of errors altogether. So, numerical damping. What is the what is mean by numerical damping in the context of numerical stability? I'll try to answer the question. We have discussed that while numerical damping refers to something that uh, if numerical damping is present, it will be the sharp features cannot be captured. Difficulty, difficulty in capturing sharp features. So suppose our solution should look like this, but due to numerical stable damping, it will be somewhat like reduced. This sharp corners or sharp features will be reduced. So in that case, in context of numerical stabilities, if numerical damping is introduced, there will be some cases like there will be sharp, sorry, there will be cases where the errors will be very high errors having sharp uh, having sharp peaks, but with a numerical damping in play, what will happen is like this will become something like it will die out, or it will reduce the amplitude, and it will uh, due to numerical damping effect, the capturing of the sharp features will reduce. So remember that what I have shown here is an error, variation of error. So this uh, cap this moment of error to sharp high values may be reduced by the introduction of numerical damping. So option A is our answer. Next question. For a stable implicit scheme, what can be said about amplification factor compared to an explicit scheme for the same problem? So the question is on implicit scheme. For a stable implicit scheme, what can be said about the amplification factor to an explicit scheme? So the question is asking simply to compare the amplification factor of implicit stable implicit scheme as to a explicit scheme. Options are: option A, it is always larger, leading to faster growth of errors. Option B, it's always smaller, providing better numerical damping. Option C, it's always equal, signifying same stability properties. Option D, it depends on specific problem and chosen parameters. So comparison between amplification factor of stable implicit scheme over explicit scheme. Try to answer the question. So our answer is we can See that amplification factor eta, sorry epsilon. So it is the ratios how the errors uh, or instabilities grow inside a scheme. So uh, from the name itself, it is asking for a stable implicit scheme. For a scheme to be stable, the uh, amplification factor should be low. Amplification factor should be low. So that we all and we have already discussed that the implicit schemes are more better than explicit schemes. So the question is here. The question is on stable implicit scheme. So combining these two, it is simple to answer the question. It's like it will be always smaller when compared to an explicit scheme. For a stable implicit scheme, the amplification factor, that is how the error grows from one iteration to another, will always be smaller to make it stable, and that will provide better numerical damping. So our answer is option B. Moving on to next question, the Jacobi iteration. So we have discussed this Jacobi and Gauss-Seidel in I think in second or third discussions interaction sessions. So the question is on Jacobi iteration method. The Jacobi iteration methods is used to solve discretized Poisson equation. In each iteration, the value at a point is updated based on its neighbors. What is the update equation? So this is the general equation, update equation for Jacobi method. So mostly the update equation meaning the general representation of a method, general equation representing a method. So here the question is asking for the update equation for a Jacobi method. Options are option A, phi nu at ij, phi ij nu is equal to phi I plus 1 comma j alt plus phi I minus 1 comma j alt plus phi I comma j plus 1 alt plus phi I comma j minus 1 alt minus f of ij into delta x square the whole divided by 4. Option B, uh, phi ij nu is equal to phi ij alt plus omega times phi I plus 1 j alt phi I minus 1 time I minus 1 j alt phi I j plus 1 alt plus phi I j minus 1 alt minus phi alt phi I j alt divided by 4. Option C, phi I j nu is equal to phi I j alt minus omega times phi I plus 1 j alt plus phi I minus 1 j alt plus phi I j plus 1 alt plus phi I j minus 1 alt minus f of I j into delta x square the all divided by 4. Option D, the update equation depends on specific boundary condition. So the question is on the update equation, the general update equation for Jacobi method. So we have already discussed the difference between Gauss-Seidel and Jacobi methods. So from that you can easily try to understand the, try to answer the question. Simply take I comma j This is I plus 1 comma j. This is I minus 1 comma j. This is ij plus 1. This is I j minus 1. So this is the grid, and also take alt as uh, n minus 1 and new as n. Then it will be easy to answer the question. Try to answer the question. Your answer is option A. So if you remember, Poisson equation will be having a function. So you only have to check for the options with having the function. So this one and this one has the function in it, f of ij, or the source term. And then here, if you see, this has taken us this negative here gives away the answer.
நெட்டு கிடைக்கல நெட்டு கிடைக்கல
So here the update equation for Jacobi method is given by option A. Whereas the omega mentioned here in these two options are relaxation factors. Moving on to next question. The McCormack scheme can be categorized as which of the following? Options are option A finite volume scheme, option B, finite element scheme, option C, finite difference scheme, option D, spectral method. So in this week's course, it has been McCormack scheme has been extensively discussed. So in which category does the McCormack scheme comes under? Options are A, finite volume scheme, B, finite element scheme, C, finite difference scheme, D, spectral methods. You can try to answer the question. You can inbox your answers. Your answer is option C, finite difference scheme, FDM. Next question. The McCormack scheme is particularly well suited for the problems involving which of the following? Options are option A, incompressible flows, option B, compressible flows with shocks, option C, laminar boundary layers, option D, turbulent flows. So this is a comparatively simple question. We have already discussed that McCormack scheme is used to solve hyperbolic equations. So in that context, if you are comparing the options, then it will be simple to answer the question. Try to answer the question. The McCormack scheme is particularly well suited for problems involving option A, incompressible flow, option B, compressible flows with shocks, option C, laminar boundary layers, option D, turbulent flows. Answer is option B, commercial flaws with shocks. So also this week's content is on solving compressible flaws. So it's just an easy question. McCormack scheme is used to suited for problems involving compressible flaws with shocks. Next question: how does McCormack scheme handle boundary conditions? Options are: it requires a special treatment at boundaries for stability. Option B: it can be directly use physical boundary values. Option C: it uses periodic boundary conditions by default. Option D: boundary conditions are not required in the McCormack scheme. So the question is on the type of boundary conditions for McCormack scheme. Options are: it requires special treatment at boundaries for stability. Option B: it can be directly use physical boundary values. Option C: it uses periodic boundary conditions by default. Option D: boundary conditions are not required in McCormack scheme. Try to answer the question. Option A, that is, it requires special treatment for boundary, special treatment at the boundaries for stability. That's our answer. Answer is McCormack schemes require special treatment at the boundaries for stability. Moving on to next question. Which of the following software packages commonly used in CFD employ the McCormack scheme? Which of the software packages commonly used in CFD employ McCormack scheme? Options are: option A, ANSYS Fluent; option B, OpenFOAM; option C, some research code utilize McCormack scheme for specific applications; option D, all commercial CFD software uses McCormack scheme? You can try to answer the question. It's so some of you might be using answers fluent or open form. So in that base, you can try to answer whether these packages contains McCormack scheme or not. So which of the software packages uses McCormack scheme? Simple question. Our answer is option C. Some research codes utilize McCormack scheme for specific applications. And also, we have already mentioned that McCormack scheme is a finite difference scheme or finite difference method. And ANSYS Fluent and OpenFOAM are mostly FVM, finite volume method based, as always. And these don't have this McCormack scheme. Also, McCormack scheme is a pretty old and specific scheme for specific purpose. So it's only being used in some in-house codes used for specific applications, kind of shock capturing and all. So uh, option C is our answer. That mostly software packages don't have McCormack scheme by default. Only some research code utilizes McCormack scheme for specific applications. Moving on to next question. The beam warming scheme is categorized as which of the following? Options are finite difference method, option B finite element method, option C finite volume method, option D spectral method. The same question was there for McCormack scheme also. This time it is for a beam warming scheme. In which category does beam warming scheme falls into? Our answer is again option A, that is finite difference method. Revamping scheme is also a finite difference method, which is mostly an ADI, that is alternating direction implicit scheme. Moving on to next question. The question asks you to find out the false statement regarding beam warming scheme. Which of the following statements about the beam warming scheme is false? Options are: option A, it's a three-level scheme. Option B, it requires storage of only two time levels of data. Option C, it uses factored approach to solve governing equations. Option D, it is a non-iterative scheme. So the question is to find the false statement regarding beam warming scheme. Try to answer the question. Actually, here, uh, options are: it's a three time level scheme. Option B, it requires storage of only two time levels of data. Option C, it uses a factored approach to solve governing equations. D, it is a non-iterative scheme. Actually, all of these are true. So there is not any false statement here. Even though this is a three time level scheme, only uh, only we need only these schemes only request to store only two time levels. So this is also true. This is also true, and it uses a factored approach. and it mostly it follows a non-iterative scheme. So all these statements are true. So uh, for this question, all the statements are true. Moving on to next question. What is the main advantage of beam warming scheme? Options are: option A, higher order accuracy in time. Option B, efficient solution due to factored approach. Option C, unconditional stability. Option D, easy implementation for complex geometries. The question is on main advantages of beam warming method. Our answer is option B, efficient solution due to factored approach. So beam warming scheme mostly follows a factored approach, and due to this factored approach, solution the solving process will be more efficient compared to other schemes. Next question. Next question is on the disadvantages of beam warming scheme. So a disadvantage of the beam warming scheme is it is options are having second order accuracy. Option B, non-iterative nature. Option C, difficulty in handling complex boundary conditions. Option D, high computational cost. So which of the following is a disadvantage of beam warming scheme? Answer is option C. Difficulty in handling complex boundary condition. So for the beam warming method, uh, a major disadvantage is that it's difficulty in handling complex boundary conditions. Moving to the next question. Which type of the iteration method is sometimes used in conjunction with beam warming scheme for improved convergence? Options are Jacobi's iteration, Gauss-Seidel iteration, option C, relaxation methods, and D, all of the above. It's already written here. Our answer is Gauss-Seidel iteration is sometimes used in conjunction with beam warming schemes to improve the convergence. Next question. For higher order accuracy in space, the McCormack scheme can be extended to a which of the following? Options are Lax-Weintraub scheme, option B TVD total variation diminishing scheme, option C ENO that is essentially non-oscillatory scheme, option D spectral collection co-allocation method. So to obtain a higher order accuracy in space, uh, the McCormack schemes can be extended to which of the following? Options are Lax-Weintraub like scheme, option B TVD scheme, option C ENO scheme, option D spectral collocation scheme or method. Answer is option C. Option B. That is TVD scheme, total variation diminishing scheme. So uh, we have discussed that in McCormack scheme, the preconditioners predictor step as well as the character step, the diffusion is happening, and such diffusion can be extended to a total variation diminishing scheme, that is TVD scheme. Moving on to next question. When compared to modern CFD methods, the McCormack scheme is considered as which of the following? Options are a fundamental building block for understanding numerical schemes. Option B, the most efficient and accurate scheme for all CFD problems. Option C, obsolete due to development and more advanced method. Option D, primarily used for incompressible and low speeds. So the question is on the position of McCormack scheme in the CFD development timeline. So, what do you consider the McCormack scheme to be? Is it a fundamental building block for understanding numerical schemes, or is it a most efficient and accurate scheme of all CFD problems, or is it a absolute due to its the development of more advanced method, or uh, it can only be primarily used for incompressible and low speed flows? Our answer is option A, fundamental building block for understanding numerical schemes. So it's based on it's even though it is absolute, it is not much used. It's a fundamental building block for understanding numerical schemes. Option A. Next question. An unconditionally stable scheme is one that which is stable for any discretization step size. Option B requires a specific step size for stability, always converges to the solution. Option D minimizes the error at each step. The question is on the basics of unconditionally stable scheme. So, when can you say a scheme is unconditionally stable? You can try to answer the question. The answer is option A. So we you have known this stability criterion is mostly based on CFL, current voltage Lewis condition, where we will be changing the step size uh, to make the step make the scheme more stable. But for an unconditional stable scheme, uh, we don't have to adjust the step size uh, to make the scheme stable. Such a scheme is called unconditionally stable scheme. Moving on to next question. When solving a system of linear equations, a well-conditioned system leads to a numerical schemes with which of the following? Options are option A, high computational cost, option B, lower round of errors, option C, slower convergence rate, option D, increased numerical stability. So we have discussed about well-conditionedness, ill-post system, all those things in the previous sessions. So in that context, so what will be the result of a well-conditioned system? Our answer is option B, lower round of errors. So while solving a system of linear equation, if the system is well conditioned, then the numerical schemes will tends to have lower round of errors. Next question. In the context of finite different methods, a higher order scheme typically implies which of the following? Options are option A, increased computational cost, option B, faster convergence to the solution, option C, reduced stability of the scheme, option D, lower accuracy compared to a lower order scheme. So the question is on higher order scheme. So which of the following uh, is implied in a higher order scheme? Option A, increased computational cost. Option B, faster convergence to the solution. Option C, reduced stability of the scheme. Option D, lower accuracy compared to a lower order scheme. Try to answer the question. We have already discussed about higher order schemes, and uh, even though higher order schemes gives better accuracy, increased computational cost is a trade-off we have to uh, suffer in higher order schemes. Moving on to next question. The scheme is classified as which of the following? Options are A single step scheme, option B two step scheme, option C three step scheme, option D none of the above. Try to answer the question. We have already discussed that McCormack scheme is having two steps: predictor and corrector. So it is having two steps. So the answer is option B, a two-step schemes. Moving on to next question. In McCormack scheme, the predictor step uses which of the following? Options are explicit formulation, option B implicit formulation, option C combination of both, option D none of the above. The question is on McCormack scheme and which kind of uh, formulation does the predictor step uses in a McCormack scheme. The answer is option B implicit formation. McCormack schemes predictor steps use an implicit formation for uh, the predictor step. question. McCormack scheme is particularly useful for the problems involving option A, steady state flows, option B, transient flows, option C, incompressible flows, option D, none of the above. We have already answered, worked out a similar problem. Try to answer the question. We have already discussed that McCormack scheme is used for solving hyperbolic equations. Also, it is used for solving compressible flows. So, this can be removed. And again, from hyperbolic from the examples of hyperbolic equations, you can easily understand transient flows can be uh, hyperbolic flows. So, option B is our answer. Option B, transient flows. Next question. Compared to lax one-drop scheme, McCormack scheme offers which of the following? Options are lower accuracy, option B higher accuracy, option C similar accuracy, and option D none of the above. The question is to compare the accuracy of lax one-drop scheme with McCormack scheme. Answer is option B higher accuracy. McCormack scheme offers higher accuracy when compared to lax one-drop scheme. Answer is option B, higher accuracy. Moving on to next question. The McCormack scheme is more computationally expensive than which of the following? Options are explicit schemes, option B, implicit schemes, option C, both explicit and implicit schemes, option D, none of the above. So remember, McCormack scheme is a two-step scheme. It has a predictor step and corrector step, and that uh, It's also an implicit scheme. So in that context, if you are trying to answer the question, it will be easy. Question is, McCormack scheme is more computationally expensive than which of the following? The answer is option A, that is explicit scheme. McCormack scheme is more computationally expensive than explicit schemes. So that's all for today. Thank you for joining. Thank you.